For more than a decade now, Google's Tensor Processing Unit, the TPU, has had this almost mythical status in the world of AI hardware. It was really the OG, the original proof that you could build custom chips to completely blow away general-purpose ones, and it was all hidden away behind Google's data center walls. But here's the thing about that. It's not magic. Not at all. It's just really, really good engineering. And so in this explainer, we're going to pull back that curtain. We're going to look right past the myth and get to the real story. The story of tough trade-offs, of real-world constraints, and the absolutely brilliant co-design that made the TPU a reality. The story of the TPU doesn't start with some grand vision for a supercomputer. It actually starts with a crisis, a huge one that was looming on the horizon. To really get what the TPU is all about, you first have to understand the problem it was built to solve. So let's rewind a bit. Back in the early 2010s, the very foundations of the computing world, well, they were starting to shake. The reliable, predictable progress that literally everyone had taken for granted for 50 years was grinding to a halt. For decades, the deal was simple. You didn't have to change your software to get these massive performance gains. Nope, you just had to wait a year or two for the next generation of chips. But that engine was sputtering out. CPU performance, which used to double every 18 months like clockwork, was suddenly on a trajectory to double every 20 years. The free ride was officially over. And this was happening right as the AI revolution was starting to demand more compute than ever before. And this led to what was basically Google's nightmare scenario back in 2013. A projection showed that just to handle the demand for all their new neural network-powered services, they would need to literally double the number of data centers they operated. I mean, that wasn't just expensive. It was physically and logistically impossible on that kind of timescale. They needed a new plan, and they needed it fast. So what do? If you can't make the general-purpose engine go any faster, your only other option is to build a brand new engine, one that's designed for one specific racetrack. And that, right there, is the core idea of specialization. And this really highlights the core trade-off. A CPU is like a Swiss Army knife. It's a jack of all trades, and it spends a ton of its energy on complex control logic just to be ready for anything. A specialized chip? It just throws all that away. It dedicates its entire energy budget to doing one single thing, in this case, the math of neural networks, with just brutal efficiency. And this was TPU version 1. It wasn't built to train new AI models. No, it was basically a fire extinguisher for that immediate data center crisis. It had a single, almost monastic focus: run already trained models, what we call inference, as quickly and as power efficiently as humanly possible. Now, the heart of the TPU is this amazing thing called a systolic array. And the best way to think about it is like a bucket brigade for math. Seriously. Imagine a big grid of little calculators. The numbers you want to process, your inputs, they stream in from one side. As each little calculator does its part, it passes the partial result to its neighbor. So this wave of data just moves across the grid, keeping every single math unit busy on every single clock cycle. It's an incredibly efficient way to do the massive matrix math that's at the very core of AI. And the results were, well, they were stunning. TPU v1 delivered anywhere from 15 to 30 times the performance of the very best CPUs and GPUs of its time, but with 30 to 80 times the power efficiency. It was a massive, undeniable validation of the whole idea of specialization. The bet paid off big time. But solving one crisis just revealed an even bigger challenge waiting on the horizon. Right, so running a model is one thing. But creating it in the first place, training it, that is a completely different animal. It's kind of like the difference between reading a book and actually writing a novel. The Spartan, super-focused, and inflexible design of TPU v1 just wasn't going to cut it for this. Training is way more complex. It requires this process called backpropagation, where the model learns by tweaking millions of its own internal weights. This means you need much more flexible hardware, and you need higher precision math. It's an exponentially harder problem, and it demanded a complete ground-up redesign. One of the key breakthroughs here was a brand new number format called bfloat16. It turns out that for training an AI, being able to represent a massive range of numbers is way more important than pinpoint precision. So by just tweaking the format, giving up a little bit of precision to get a much, much wider range, bfloat16 gave them exactly what they needed, and it was far more efficient to build into the silicon. It was the perfect trade-off. So the result was TPU v2, and it was a radical departure. It was way more programmable, it had super fast memory, and, most importantly, it included a high-speed inter-chip interconnect, or ICI. This was really the first clue that Google wasn't just building a chip anymore. They were starting to build a system of chips, all designed to work together as one. And that's exactly where the story pivots. The focus shifts from the performance of a single tiny chip to the performance and, critically, the economics of an entire data center packed with them. By the time they got to the fourth generation, the whole game had changed. The guiding principle now was something called total cost of ownership. It's not just about how much the silicon costs up front, it's about power, it's about cooling, reliability, and how effectively you can use thousands of these chips over their entire lifespan. Every single design decision was now being looked at through this economic lens. So this is how you build an AI supercomputer, layer by layer. It starts with the chip itself. Then you link those chips together inside a single rack. And finally, you connect hundreds of those racks together into a massive pod of over 4,000 chips. But connecting all of those racks flexibly and efficiently, that required a totally new approach. The answer was something straight out of science fiction: optical circuit switching. Think of it like a gigantic, programmable telephone switchboard. But instead of old copper wires, it uses thousands of microscopic mirrors to physically steer laser beams around. This let them dynamically rewire the connections between entire racks in milliseconds, all controlled by software. It was the absolute key that unlocked unprecedented scale and flexibility. Okay, so we've talked a lot about hardware, but the hardware is really only half the story. The TPU would be completely useless without an equally sophisticated software ecosystem that was built right alongside it from day one. So when a user submits a job, this breathtakingly complex dance happens behind the scenes. Google's cluster manager finds the available chips, the optical switches reconfigure themselves to connect them, then a compiler called XLA takes the AI model and automatically slices it up to run across thousands of individual chips. The key thing to get here is that once the job starts, there's no central brain. Every single chip knows exactly what it needs to do and runs in perfect sync. This execution model is called SPMD, which stands for Single Program Multiple Data. And honestly, the best analogy is an orchestra. The compiler gives every single musician the entire symphony score, but the violins know they only play the violin part and the cellos only play the cello part. This lets programmers write code as if they're targeting one giant virtual device, while the software handles all the immense complexity of actually distributing it. And so we come full circle. We started this whole thing talking about the myth of the TPU, this idea that it's some kind of unobtainable magic, but the reality, as it turns out, is way more interesting. The real magic isn't some single brilliant breakthrough. It's the relentless, decade-long process of co-design. It's the hardware engineers designing circuits with the compiler team in mind. It's the software engineers writing schedulers that actually understand the physical layout of the network. Every single piece, from the number format to the optical switches to the compiler, was designed as part of one cohesive, evolving system. At the end of the day, the story of the TPU isn't about one grand decision. It's about hundreds of smaller, deliberate ones that all combine to create something truly extraordinary. And that leaves us with a fascinating question for the future, doesn't it? As the demands of AI continue to explode, forcing us to rethink everything all over again, what will the next 500 of those ordinary, careful decisions look like?